everyone, it's Justin again. In the last lesson, we learned about translating the graph of 1 over x. Now, let's look at this graph with another type of transformation, reflections. By the end of this lesson, you should be able to identify reflections of reciprocal functions in graphs and equations. First, we'll review the rules of reflections using functions we know. We'll use that knowledge to explore the effects of reflections on reciprocal functions, and then we'll practice a couple of examples. Let's start with reviewing reflections. We talked about reflections a few units ago, but if you don't remember the rules off the top of your head, it might be good to make a note of these somewhere. For a function f of x, a reflection across the x-axis can be written as negative f of x. A reflection across the y-axis can be written as f of negative x. And a reflection across both the x-axis and y-axis simultaneously takes both of the previous negatives, which makes it negative f of negative x. Let's try reflecting the square root of x, a function we already know pretty well, to see why reflections on the graphs are related to negatives in the equation. According to this rule, to reflect a function across the x-axis, we have to make the entire function negative. In this case, that's the negative square root of x. The square root of 1 is 1, make that negative, and the output is negative 1. Square root of 4 is 2, make that negative, and the output is negative 2. So, changing the sign of the whole function will flip all these positive outputs to be negative. The result is this reflection across the x-axis. To reflect this graph across the y-axis, we need to make the input negative. We put a negative sign on the x wherever it appears inside the function. Here, this ends up being the square root of negative x. In this new function, an input of negative 1 gives us the same output that we got from positive 1 in the original function. The result here is a reflection over the y-axis. And if we wanted to reflect this across both the x-axis and y-axis simultaneously, we would put a negative on both the inside and the outside of the function. With this example, that would be the negative square root of negative x. An interesting fact is that if reflections across the x-axis and y-axis happen one after another, it doesn't matter which reflection we do first. Why is that? Well, whichever negative we add first, we end up with a negative on the outside of the function and a negative on the inside, so we still get the same result. So as we move on to talking about reflecting 1 over x, remember that the axis we use for reflecting depends on whether the negative happens on the outside or inside of the function. And if you see a negative on both the outside and inside, that's a reflection across both axes. Here is the graph of 1 over x. According to our rule for reflecting across the x-axis, we would put a negative on this equation. So the reflection of 1 over x across the x-axis would be negative 1 over x. What do you think the graph will look like after this reflection? Pause the video and think about that question. Ready to see what it looks like? Let's look at some specific points again. Reflecting the point 1, 1 across the x-axis would give us 1, negative 1. And reflecting negative 1, negative 1 would give us negative 1, 1. We can verify that these reflected points are in the right places within the equation of our reflected function, negative 1 over x. For example, plugging in negative 1 gives us negative 1 over negative 1. Since there are two negatives, this would come out to be positive 1. So the point negative 1, positive 1 is indeed on the new graph. Here's the entire graph reflected. Did you notice that the function's asymptotes haven't changed? Even after the reflection, the asymptotes are still at y equals 0 and x equals 0. Next, let's try reflecting across the y-axis. Our rule for this reflection tells us we should substitute x with negative x in this equation, which would give us 1 over negative x. What do you think the graph will look like after this reflection? Pause the video and think about it. Ready to see if your guess is right? Think about each point reflected across the y-axis. Here is the reflected graph. But hang on a second. This looks exactly like the last reflection. Check out the two equations for these two reflections. It doesn't matter whether a negative sign is attached to the numerator or denominator of a fraction. That's just the same as having a negative sign in front of the fraction. So these reflections give us the same equation. That's why the graphs end up in the same place. And again, it's worth checking the asymptotes. Have they changed this time? No, they have not. It looks like the asymptotes of 1 over x do not change when reflecting across either the x-axis or y-axis. Now let's try reflecting across both the x-axis and y-axis to see what this graph will look like. Can you make an educated guess on what will happen? You can sketch a graph in your notes, or you can trace the path you think it will take on the screen. Pause the video now and make your guess. Ready for the answer? As we discussed before, when we're doing reflections across both axes, it doesn't matter which way we reflect first, so we can start with either axis. Let's reflect across the x-axis first, and then the y-axis. We actually have exactly the same graph we started with. Remember the rule that reflecting across both axes is the same as putting a negative on the inside and outside. Try applying this rule to 1 over x to see why this happens. If we put two negatives in this fraction, those negatives will cancel each other out, and we'll be left with 1 over x, which is exactly the function we're reflecting in the first place. We're almost ready to move on to some examples, but first, let's review what we've learned about reflecting the graph of 1 over x. Let's make a list of properties so we can refer back to it later. For the function 1 over x, reflection across the x-axis is equivalent to a reflection across the y-axis. Reflection across both axes doesn't change the function's equation. And reflection across either axis doesn't change the function's asymptotes. Remember these properties. These will help a lot in the examples we'll be doing next. All right, here's our first example. G of x is a reflection of f of x equals 1 over x across the y-axis and then across the x-axis. What is the equation of g of x? Can you remember the rules for how to reflect a function? To reflect across both axes, we have to put a negative on the inside and outside of the function being reflected. That gives us negative 1 over negative x. But the two negatives will cancel each other. We're left with the same function we started with, 1 over x. This is consistent with our second property of reflecting the function 1 over x. Reflection across both axes doesn't change the function's equation. So the equation of g of x is also 1 over x. We'll do one more example. Which of the following transformations could change the vertical asymptote of the function f of x equals 1 over x? Shifting one unit to the left, reflecting across the x-axis, or reflecting across the y-axis? Again, it's useful to remember our list of properties when reflecting 1 over x. Do you remember which property can help us with this question? Reflecting across either axis doesn't change the function's asymptotes. This question is asking which transformations will change the vertical asymptote. And two of these options are reflections, which do not change the asymptotes. That means the only possibility left is the first option, shifting one unit to the left. If you recall from the last lesson, a horizontal shift does in fact move the vertical asymptote by the same amount. So this is our answer. In this lesson, we talked about the reflections of the graph 1 over x. Next time, we'll talk about one more kind of transformation we can apply to 1 over x, dilations. See you then! Hey.